Okay, welcome everybody. Today we are having a Brazilian representation. He's a PhD student, Nicolas de Aguiar Alves. Maybe I pronounce really bad, so please correct me then. He's going to speak about the sky as a scale in the horizon. So, Nick, all yours.
Thank you very much. Thank you for the invitation. And yes, I'm going to talk about this new perspective we're trying to bring to asymptotic symmetries of thinking about the sky as a Kelvin horizon. Uh, and to give a bit of context, I'll first talk about uh, much of what is known about infrared physics and the interest that has been in infrared physics over the last decade or so. And to start with, there are some references in the archive which I think may be interesting. The first of them is more of a seminal reference, which is Strominger's lecture notes on infrared structure, which are where I first learned these topics. And it is mostly aimed at high energy physics, so it may be more suitable for most of the audience here. For most of the things that I'm going to talk about, I'll be based a lot on my recent paper, which is the Skies of Horizon with Andrea Landulfo, my advisor. And there's also my set of lecture notes, which is more directed toward relativists. I come from relativity, so I had a hard time learning through Strominger, and I wrote my own version in the hopes of making it easier for people who are also coming from more from the gravity side than from the field theory side. So for further details, you can check this reference here and the references within them. But that being said, let me get started into the actual physics. So the first thing that I find very interesting about all of these ideas is a mere coincidence that you can find at the level of special relativity, because when you consider special relativity, something that most presentations of the theory actually make very central is the role of the Lorentz group. So you have this group of symmetries, which I usually write as SO plus 3, 1, which is the fancy group theoretic name we give to the Lorentz group. Now, 3 and 1 just mean that I'm using the certain signature in spacetime. I usually write minus plus plus plus. So we have 3 positive, 1 negative. The other symbols mean O for orthogonal. So this actually preserves the metric, and this is the meaning of orthogonal. The plus means isochronous, orthogonal, sorry. Or is this a right in English? I think it's something like this. Maybe I'm adding an extra H here, but anyway. So it doesn't flip the time orientation. And this S is for special, which means I'm not flipping the space orientation either. I don't have parity transformations in here. So this is the simplest version of the Lorentz group. It's the continuous version that is connected to the identity. And this is one of the most important groups when you're studying special relativity. That this gives you what are the linear transformations that preserve the Minkowski metric. But something that is particularly curious about it is that this group does not appear only in relativity. If you're getting into group theory and coming from a direction that involves more of either differential geometry or maybe conformal field theory, you may also notice that this same group also goes by another name, which is sometimes written as a cell 2C over Z2, which is a fancy way of writing a different group. And in this version, it is typically called the Möbius group, or more importantly, the conformal group on the sphere. So what I mean by this is that this is the group of transformations that preserve angles on the sphere. So if you take the 2 sphere here and you map each point to some other point on this range sphere, this transformation is going to preserve all angles between curves on the sphere. So this is what we mean by conformal. And this is particularly interesting because this is a very special sort of transformation that can lead us later to many new ideas, and in particular has led to the development of conformal field theory, which is one of the most prolific topics in field theory. And this is in principle just a coincidence. It is this happy coincidence that I find particularly curious, in which you write the Lorentz group in 4 dimensions. And for some reason, this group turns out to be the very same thing as this quite geometrical group in the 2-dimensional sphere. So they just happen to be the same. And at least in principle, that there's no clear reason for why you need to have that. But upon a closer inspection, you can actually understand what is happening in here, why these guys need to be the same thing. And what happens is the following. If you pick an observer in Minkowski spacetime, so we usually call them Alice and Bob in relativity, so let's just call him Bob. You pick Bob, and Bob has this past light cone, which is the collection of all events which can interfere with Bob right now. So you take this light cone, and then this is going to be the surface of this light cone is going to be something at fixed advanced time. So this has time plus radio distance equals constant. And by increasing the distance to Bob, I can go toward the outer directions of the light cone. I can go back into the past of the light cone. And at each fixed radius, I have a sphere over here. In particular, if I take the limit in which the radius goes to infinity, I'm going to just push back into the far past of this light cone. I'm going to go back to infinity. And there at infinity, I'm going to have this sphere, which is the limit of this light cone. And this is what we usually call the celestial sphere, so the sphere at infinity. And this has a physical interpretation because, for example, if Bob is watching the night sky and there are many stars in the sky, which is looking at, these stars are, for him, coming from this celestial sphere. So if I draw this same picture of him gazing at the night sky in a Minkowski diagram, what I'm going to have here is exactly that he is receiving light that is traveling along his light cone, hence the name light cone. And the stars are all here at the sphere at infinity. So I am, of course, taking an approximation in which the stars are infinitely far away. But the basic idea is this, that they are located at infinity and their light travels along the light cone until they reach Bob. A question that is particularly nice to ask about how Lorentz transformations behave is the following. I can have here 2 observers now, so I'm going to have Bob and I'm going to have Alice this time, so I'm going to draw her a little bit different. And each of them have their very own light cone, and they see the stars in here in some way. So, okay, this is terrible. Let me draw this again. Here we go. And each of them may see the sky in a slightly different way. So Bob is seeing the stars in these positions. Maybe Alice is actually seeing them in a slightly different way, but they see the same stars. Since there are 2 observers, I'm going to assume for simplicity that they are right now related by some Lorentz transformation. So maybe they are rotated relative to each other. One of them is looking towards the north, while the other one is looking towards the east, or something like that. Or maybe they are boosted relative to each other, or something like that. They are related by a Lorentz transformation. And I may then ask, how do the positions of the stars that each of them see relate to each other? Now, if this Lorentz transformation is a rotation, this is going to be particularly simple because a rotation among them has to become a rotation among the stars. So if I just rotate Bob relative to Alice, the stars are going to rotate in the same way as well. So rotations go to rotations. So a rotation in Minkowski is going to a rotation in the sphere. Now you have also the more complicated case in which you have a boost. And if you have a boost in Minkowski, this is going to lead you, and you can do the calculations in detail to check this, it is going to give you a conformal transformation in the sphere, a more general conformal transformation. So if you do a Lorentz transformation in between 2 observers in Minkowski spacetime, their celestial spheres, the position of the stars that they see on the heavens, is going to be related by a conformal transformation on S2. So this is why, in a sense, you have that the same group must be present in these two descriptions. So you have the Lorentz group in the bulk, you have the Lorentz group for observers in the middle of Minkowski spacetime. And when you push it back to infinity, what you have to get is a conformal transformation in this sphere, which is described by the very same group. So if you just draw the sphere at infinity and ask how the positions of the stars shift, if they are rotating, it is going to look something like this. So the stars just rotate. If they make a boost, it is going to look a bit more like this. If you are moving toward the upward z direction, you will see all the stars shifting towards the North Pole, except for the star that is just behind your head. So you have this relation of how Lorentz transformations act on infinity, and they act precisely as conformal transformations. Now, this is something particularly interesting because since we have a conformal group, let us say for free in Minkowski, maybe we can explore this and try to deal with a conformal field theory in this celestial sphere. So this is the basic idea behind what we call the celestial holography program. You're going to try to map a theory that lives in the bulk of Minkowski spacetime to a holographic dual in the sphere that lives at infinity. In the sphere, you already get this conformal symmetry. You already have this conformal group in the sphere. And this is the starting point for you to try to think about conformal field theory and stuff. However, the sphere is a two-dimensional manifold, which means that this group here is actually just part of the story. So this guy here has 6 degrees of freedom. It is a group with 6 parameters. But when you're working with two-dimensional manifolds, you can map them locally to the complex plane. And in the complex plane, the conformal transformations are any holomorphic transformation, which is a much larger group. You can, in conformal field theory, usually don't work only with the Lorentz group. You actually go to what we call the local conformal algebra, which has infinitely many degrees of freedom. And it's this structure which makes two-dimensional conformal field theory so rich. So we would like to try to exploit this somehow. And a natural question is then whether we can get larger symmetries at the sky, or if we're restricted to only this global conformal group, only the transformations that are defined on the whole sphere, rather than the transformations that are defined only locally, which would be the case for this so-called local conformal algebra with all of the holomorphic, or actually meromorphic functions. Now, let me just see here because, okay, yeah, the Zoom screen is in front of the new page button. Anyway, so the first step to proceed on this is that instead of working with only the Lorentz group, we may try to consider the larger Poincare group in Minkowski spacetime. Now, the Poincare group is composed of the Lorentz group and some more transformations. So I usually call it ISO plus 3-1. So this I is for inhomogeneous. And what I'm going to do now is that this guy is going to be the Lorentz group times R4. Now, this R4 are the translations that I have on spacetime. So both my spatial translations and my time translations. If you want to be a bit more precise, this product here is actually what we call in group theory a semi-direct product, which is a particular way of combining two groups into a new group. Now, these details are not going to be so important for us, but I'm going to draw it in this way just to make some structures more repetitive later on. But what's important is just that this is a specific way of combining two groups into a new group. And this is how the Poincare group is formed. You take this specific structure between Lorentz transformations and translations. And one way of writing this in a more matrix-like notation would be that you map some event x to a Lorentz transformation acting on x plus a translation. So this is the structure that we have for this group. And then we may ask, how exactly did these new transformations, the translations, act on infinity as well? And to see this, one way, a quick argument that is not very rigorous, but it gives you the broad idea is the following. we have here, so we take Bob again, and his past flight cone is defined at constant advance time, which is some coordinate v equals to t plus r, which is a constant. Of course, r is just the radius in spherical coordinates, so I can also write it in terms of Cartesian coordinates in this way. And then I can start asking, okay, if I do a translation in each of these coordinates along t, along x, along y, what exactly happens to my coordinates in here? First, we have a t translation. In this case, the t translation is just t goes to t plus, let's say, epsilon. And this is going to lead to v goes to v plus epsilon, because you just have this linear dependence on t. So you don't change anything else, you just shift v by a constant. Oops, where am I here to click for a new page? The Zoom controls are again in front of me. Here. Okay. Next, we can try for a next translation. And for the x translation, what I'm going to do is x goes to x plus epsilon. And this time, the change I'm going to have in v is going to be v goes to v plus epsilon dv dx. And if you just compute this partial derivative, I'm taking here a linear approximation. But if you just compute this, what you're going to have is something along the lines of epsilon times x over r plus stuff. And I can just rewrite this using spherical coordinates as sine theta cosine phi plus stuff, where these are the standard angles in spherical coordinates. If I just wanted to do this for different directions, I could do, for example, y goes to y plus epsilon, and this would give me something like v goes to epsilon, sine theta, sine phi, etc. These transformations also, we're not going to change the order coordinates that I have in infinity, so they are shifting my my retarded time. So when I move from one light cone to another, so I'm moving Bob from here to here, and there's a shift in my light cone, and there's a shift in what exactly is the v direction. But it doesn't really have a modification in the sphere components, in the sphere coordinates, when you push things back to infinity. So this is all transformations you get. In other words, translations will act on infinity according to the following rules. You just map the angles to the very same angles, you don't change them. While you do change the constant advance time along your light cone, and it is going to go something that looks like the following. You're going to have something like this, plus minus L. Where this YLM is a spherical harmonic. So for L equals 0, what we're going to have is just Y0, 0, and this is a constant. So nothing particularly special. While for L equals 1, what we're going to have here is something along those lines that I was writing earlier. So we have sine of theta, cosine of phi, sine of theta, sine of phi, and cosine of theta. So this is just the structure. For spatial translations, you get spherical harmonics with L equals 1, while for time translations, you get spherical harmonics with L equals 0. And this is the structure you have for translations. Now, when I write things in this suggestive manner, it is sort of natural to wonder what happens if I try to consider more general transformations in which I just lift this restriction of stopping on 1 and just let the spherical harmonics run into whatever they want instead of stopping specifically at L equals 1. Now, when I do this, what I'm changing is the following. For L smaller than or equal to 1, I have 4 parameters. So I'm going to have 4 values of epsilon here. I'm going to have epsilon 0, 0, epsilon 1, minus 1, epsilon 1, 0, and epsilon 1, 1. While for arbitrary epsilon larger than or equal to 0, this is going to give me a much larger structure. I'm going to have actually any function on the sphere. And I have a much larger choice of coefficients, epsilon, lm. So if I allow for this, if I let you consider this larger group of transformations, what I'm actually going to find is this group SO plus 1 times infinity S2. And so far, this is just some play with how exactly I'm defining those transformations. And this doesn't really mean anything. So there's no reason for me to consider this group any more seriously in relativity, except for the fact that this analysis, while I'm telling it in this way, I'm not telling in the historical approach. And what happened historically was that Bondi, Metzner, and eventually Sachs were concerned with the symmetries that you get for asymptotically flat spacetimes at infinity. So you have some spacetime in which you have, for instance, maybe a black hole, maybe a star, anything compact, and you go very far away from it. And here at infinity, you start asking yourself, what are the symmetries that you have away from all of those things in general relativity? So since you're far away from everything, you can in principle think, well, far away from all sources, this should be somewhat like special relativity, and I would expect to get the Poincare group, which is the group that I actually find in relativity. But what they found was actually much more interesting, was that the symmetry group you actually get in this sort of spacetimes is what we nowadays call the BMS group, which is exactly this increased group that I discussed right now. What happens is that when you go to infinity, that restriction on L equals 1 becomes a little bit unnatural. And what you get in a general spacetime is actually this larger group, which we call the BMS group. So you get this larger amount of symmetries in a very natural way. And what is actually unnatural is trying to look for Poincare in a general spacetime. If you are in a Minkowski spacetime, you have a very natural way of defining Poincare because you can just work in the bulk and you pick your bulk symmetries. And when you push to infinity, you're still going to have Poincare at infinity. So you define it first in the bulk and then you go to infinity. But when you're working in a more general spacetime, for instance, with a black hole, then the interior of your spacetime is breaking the Poincare symmetries. For instance, if you have a black hole or a star or something, then I certainly do not have translation invariance, because if Bob is here at a certain distance from the black hole and I push him further away, now this is certainly not a symmetric transformation, because he will notice that he is further away from the black hole, maybe because he's feeling different tidal forces and something like that, but he can notice the difference. So you no longer have Poincare invariance in the bulk. At infinity, when you're far away from everything, you can get some symmetries that resemble what you have in Minkowski spacetime, but you're not really able to get specifically Poincare. You are forced to take this larger group, and within this larger group, you're not capable of selecting what is the correct version of Poincare group. What happens is that Poincare is indeed inside BMS, but you have many versions of the Poincare group inside BMS. So, for instance, if I take some element of infinity S2 and then I apply this on Poincare, and then I undo my infinity S2 transformation, this is going to give me something that is also Poincare, but it is different. So Poincare prime, so to speak. So I have many different copies of Poincare inside the BMS group, and I don't have really a preferred way of saying which one of them is the right one. So I'm forced to work with this larger group. What we get then is the structure in which I have Lorentz transformations, and I have this increased number of translations. We call them super translations. So super is just because we have many more of them. So they are a generalization of translations. This has nothing to do with supersymmetry. In fact, the BMS analysis happened something like 10 years before supersymmetry is started becoming something popular in the 70s. So just a coincidence in name and nothing really relating both ideas. Now, so far, what I have argued is that the symmetries at infinity are this BMS group. But it is not really clear what this means. So I say that if I try to compute the symmetries in a certain way, what I'm going to find is that infinity is defined up to this transformation. So I have this freedom in how I define infinity, but it is not really clear what exactly this means physically. So do I have any physical interpretation for this? Is this just a mathematical curiosity, or is this something that actually, let us say, matters somehow? And the answer to this would come much later, arguably would come at around 2013, 2014, with Strominger and collaborators who noticed a relation between this BMS transformations and what is known as the Weinberg soft graviton theorem. So the basic idea is the following. If you have this BMS symmetries, we would expect that the symmetries are somehow related to a conservation law. There's a something reminiscent of Netter's theorem. Now, this relation is not really as straightforward as I'm pretending it is, exactly because these are actually asymptotic symmetries. These are symmetries at infinity. So they are symmetries in a slightly different way than we're actually used to. But you can actually argue that within some assumptions, you have conservation laws associated to the symmetries. Now, if you have conservation laws, it means that you have some sort of charge that is not changed between late and early times. And I can write this differently in terms of an S matrix by saying that if you apply this charge under quantum theory and then you evolve time, this is the same thing that you make a time evolution with the S matrix and then you apply the charge. So this is just the expression of charge conservation in quantum mechanics using the S matrix. Now I can take this expression and I can just throw it in between any two states that I want in my quantum theory and write this in this way here. So I just take any two states in some quantum theory I'm working on. In this case here, I'm going to need this to involve gravitons in some sense. I'm going to apply these charges that I obtain from the BMS symmetries, and then I'm going to apply the S matrix, and I'm going to derive what exactly this thing means. And it was shown by Strominger and collaborators that this actually leads to what we call the Weinberg soft graviton theorem. This theorem is a result, well, of course, by Weinberg and that he got in 1965 without thinking about anything related to BMS stuff or anything of the sort. And what Weinberg was considering was, well, you just take a bunch of elementary particles, you let them scatter, and eventually you get something on the other side. And I want to consider what happens to this scattering amplitude when I add one graviton with an energy omega, and omega is very small. The result that Weinberg found was that you actually get something that is just some factor, I'm going to write it as O, over this energy omega, times your original scattering amplitude without the extra soft graviton, plus corrections. Now, these corrections here are smaller than 1 over omega. So this is why omega being small is important. This is the dominant contribution when you make this expansion in omega for small omega. And you get this relation here. So this is what we call the Weinberg soft theorem. You have this factoring property. If you add an extra graviton, everything you have to do to compute this new amplitude is to multiply by some factor, which we can't write explicitly. You have to multiply by 1 over omega. Then you write the original amplitude without that extra graviton, and you're going to have some corrections at lower orders in this small omega expansion. So this here is something that is picking this symmetry due to this calculation by Strominger that shows that this BMS symmetries lead you to this. This means that if you start with the symmetries, you actually get dynamical consequences. You actually are going to compute some processes in your theory that involves a graviton, and these processes are going to be related somehow. So the physics of how this guy here happens is actually related to all of these guys, thanks to the BMS symmetry. So the BMS symmetries have a dynamical consequence. They imply something on how your theory is supposed to behave. This is also particularly interesting on a different thing, because another result also from the 60s and 70s, it's from
Nick,
70. Yes.
Nick, sorry, before you continue with that, what does it mean the omega very small from the point of view of the BSM group? I mean, here you have now like the soft theorem of Wagner's soft theorem is like a scale that is given by this omega. So, do you have like a limit also in the BMS group, or what the relation this omega and the what you said before?
Mhm. Yes, you have a limit hidden in the BMS group, because what I'm doing in BMS here is I have, for instance, a black hole or something in the middle of spacetime, and I'm going very far away up here to this region that I'm going to call infinity. We usually draw in Penrose diagrams with this diamond shape. And this here is at some distance r. So this
Ah,
radio distance r.
yeah,
And I'm taking this limit as r goes to infinity. So I'm going at very large distances. Now,
yeah,
very large distances are equivalent to very low energies. So the
yeah, yeah,
relation
like
I'm going to have
shifting.
between these two guys is going to be this.
Okay, okay, yeah, yeah, yeah. So they are like shifting the energy due to you are going far away. Okay, perfect. Okay, I
Yes,
understand.
I'm
Thank you.
going to the infrared limit. So very large distances, very small energies.
Okay, okay, so perfect.
Right. Uh, and this idea is going to also turn out to be related to this other result from the 70s, which this one is due to Zitovich and Ponarev, which we would later call the memory effect. Now, Zitovich and Ponarev were working in another completely unrelated stuff in principle. And what they were considering was, well, maybe you have some stars in the middle of your galaxy, uh, close to the core of the Milky Way or something like that. And these guys are interacting gravitationally in a very complicated manner. And eventually, let's say they just go out. Maybe two of them become bounded in some way and start orbiting each other or something like that. And in this process, in this scattering process, the stars are going to emit gravitational waves, which is a calculation you can do in standard general relativity at the classical level. Now, what they found is that if you grab now these gravitational waves, you can just let two probes here at infinity. And when the gravitational wave passes through them, this distance between them is going to oscillate. So if I make a plot here of the distance between them versus time, I'm going to have this oscillation due to the passage of the gravitational wave. And what they found is that typically for these sorts of things, the actual shape of the oscillation is not going to be just this sinusoid thing, but actually it is going to look a little bit more like this, in the sense that you have these oscillations, but you also have a finite change in the overall distance between early and late times. So you start with your probes at a certain distance, the gravitational waves are coming in. After the gravitational waves passes, these probes are at a different distance. So in this sense, they remember the passage of the gravitational wave. This is what we call the memory effect. And this turns out to be an expression of the very same physics that lies behind the Weinberg soft graviton theorem and the BMS symmetries as a consequence. So a way to see this, and this particular view was given by Strominger and Zildovich in 2016, I think 2016. And the basic idea is the following. You just take Weinberg's scattering amplitude. So I have something like this, and I'm going to interpret these particles as if they are the stars or something like this. And they are emitting this graviton, which is exactly my gravitational wave. To compute this gravitational wave, what I can do is, in a sense, divide by the amplitude without the gravitational wave. So this is going to take out the part of the amplitude that is describing the scattering of the stars and give me just the gravitational wave generated by this scattering. And this can be made more precise when you're working with the generation of gravitational waves in a sort of a quantum field theory approach. So this here is going to give you exactly the gravitational wave, which I'm going to let me represent this way here. So you have some source and you have the gravitational wave leaving you. And using that soft graviton theorem, what you have is that this thing here should be just that factor over omega plus corrections. So something like this, which means that we can use Weinberg's theorem to compute what is the gravitational wave generated through this scattering process. And here I'm interpreting these stars as if they were elementary particles, and this makes sense in this case, because since I'm working with very small omegas, which means very large distances, both a star and a point particle look essentially like a point. So they sort of behave as if in the same way. And you can actually start with this calculation. Now, this is going to give me what is the gravitational wave in Fourier space. So here I have the energy. What I can do now is just do a Fourier transform. And this is going to give me something that looks like 1 over r. So this is delta hij. This h is the perturbation in the metric. So it's going to be the full metric is going to be mu equals the Minkowski metric plus this perturbation. And we're going to have something that's proportional to this thing here. It's going to be the derivative of the quadrupole of the source at late times minus the second derivative of the quadrupole at early times. It's something that looks like this. Important thing is this thing here is for those sorts of processes typically not zero. So what we're going to have here is exactly that the change that you're going to get in this h over very long time. So here is hij at late times minus hij at early times is not going to be zero. The reason for this is that when you take the Fourier transform of 1 over omega, this is going to give you the Heaviside theta function. So if I have this 1 over omega in Fourier space, what I get in real space is going to be this step function. So when I take the Fourier transform of this complicated waveform in Fourier space, this contribution here is going to give me exactly that sort of finite change over time. So when I take the difference between late times and early times, I'm going to have this finite effect here. And this is a prediction on gravitational wave physics. Now, I'm sketching the argument that you can make with the Weinberg soft graviton theorem, but you can also make precisely, you get to the exact same result if you start with plain classical general relativity and just work with standard gravitational wave techniques, such as, for instance, just writing the Einstein equations in that typical linearized form, and solving these equations by using a retarded Green's function, you're going to get to the very same result. It's going to look something like this, depending on how many approximations you make. This here is with more approximations than you need,
Nick,
but it's the version I remember by. Yes.
how small is this step delta H? I mean, it can be measured the LIGO, or have already done? No.
Yeah, the difficult thing with measuring this at LIGO is not really about the it is sort of about the size of this, but the most important thing is about the frequency. So this happens, this is an effect that is related to very small frequencies because it occurs in this way that
Mm,
it is 1 over omega. And at very small frequencies, you have this problem that you also have other gravitational contributions, such as the gravitational field of the Earth, which is much more
mm,
important.
okay.
So it is difficult to see this at LIGO. As far as I know, I don't know much about the experimental aspects of this, but from what
Mm,
I've read, there is expectation that future gravitational wave observatories are going to be able to measure these sorts of things uh, at each event. So if you
mm,
have a merger of black holes, maybe LISA will be able to measure these things. For instance, because the satellites of LISA would be a triangle or something like this, and then the gravitational wave
mm,
passes, and it is going to distort them
mm,
somehow or something like this, and they're going to have this fixed change.
mm. Uh,
And LISA is going to be more sensitive to these low frequencies.
mm,
At LIGO, there is still some hope because what they can do is this process that they call stacking, if I remember correctly, which is you just grab data from many different events. You need about 2,000 or so. And by combining these 2,000 events and doing some data analysis, you can, in principle, search for these sorts of effects in the combined data set. But we still haven't reached 2,000 events yet. So far, we haven't seen this, and we wouldn't expect to because LIGO is not sensitive to these frequencies, and we don't have enough data on LIGO to make this stacking procedure. But it is expected that we will be able to see this on LIGO on the future or on other gravitational wave
mm,
observatories on individual events.
okay. 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 I guess that's the motivation, Celestial, that you are close to reality. Thank you, Nick.
Yeah. Uh,
Nicholas, sorry, I have a
yes.
question. What's the physical meaning of this memory effect? I mean, it seems like it should change the momentum or something like that, right? I mean,
It in the gravitational case, it doesn't really, because what happens here is essentially that you start with this. You start with this some value of h. So let's say
yeah.
let's pick the polarization plus, for instance. So you have polarizations with plus and x. Let's say plus. So what you're going to have here is that the h plus can start at some value. Then as time passes by, you're going to have this change, and eventually it stops at a different value. So physically, what this means is that this h plus is correlated to the physical distance between these two detectors. So maybe this guy is at a coordinate distance d, but the physical distance that you measure between these guys are going to be d, the coordinate distance, times 1 plus h plus, or something like that. So as time passes, the distance between them increases because space is expanding in that region. And
Okay.
what you're going to have is something like this. So you're going to have that space-time is going to remember that the wave passed and stretched space, and it left a permanent imprint. So it is going to keep them at a separate distance. In the gravitational case, they stop. But you also can make similar calculations in other theories, for instance, electromagnetism, and you get a change in momentum. For electromagnetism, this is actually a quite fast calculation. So you just start with something like this. So you start with the Lorentz force. I'm going to assume that the velocities are very small so that I can drop this term. Now I have this thing here. What I can get now is that m times, so the change in velocity that I'm going to have on my test particle is going to be q over m times the integral of the electric field over time. So if this integral is non-vanishing, then my particle will get a kick in velocity in between early and late time. So it gets a change in momentum. In the gravitational case, you have different symmetries because it is a spin 2 theory rather than a spin 1 theory. And instead of a kick in velocity, you just get this shift in distance. But the idea is simple. Does it make sense?
Yes. Okay. Thank you.
You're welcome. So this is the much of the interest that has occurring in the era in the last many years has been due to this relations between many topics. And what I find interesting and where my work starts getting in is when you start looking at other situations. So far I've talked mainly about asymptotically flat spacetime, so spacetimes that have an isolated object and then you go very far away from it. But you can also do similar ideas in other sorts of spacetimes. So for instance, I can draw here the zeta spacetime. We usually draw it as a square. This is the Penrose diagram. And if you slice the zeta spacetime in the way cosmologists usually do, so flat planes, what you're going to have are slices that look like this. So you only cover half of the zeta spacetime using flat planes. And this boundary here is what we call the cosmological horizon. As you take the limit in which time goes to minus infinity, go as far back as possible, you're going to reach this horizon here. And there's nothing particularly special about this when you take a look at the zeta as a whole, because it's just a choice of coordinates that only covers this half here. But this is an interesting horizon because you can have causal effects in here. So for instance, if you are in this region here, you'll never be able to send any signals to someone who is in this region here. And you have this causality constraints. Furthermore, if you are in this region here, which is the region of cosmological interests, or cosmological models usually live in this region, then you have this new surface here, which behaves as a boundary. So it is a boundary at a finite distance, but it is a boundary in the sense that it bounds the region of spacetime you're interested in. And there is this work in mathematical physics, in algebraic quantum field theory in co-spacetime by Dappiaggi, Moretti, and Pinamonti, in which they consider the symmetries on this boundary here, and they get to a group, which I like to call the DMP group after them, and they find it to be SO3 times infinity S2 times infinity S2. Now, this reminds a little bit of the BMS group because you have this SO3 here, not a Lorentz group, but almost. And you have these factors here, but it is still notably different. So you have two factors of infinity here. This here is not the Lorentz group, it's just the rotations. And it makes some sense when you take a look at the zeta, because the symmetries in the zeta are not the Poincare symmetries. They are instead what we call the de Sitter group. And when you take a look at this group and you say, no, I actually only want the symmetries that preserve this boundary. So if a symmetry, if one of the transformations preserves the zeta but takes me from here to here, I'm not really interested because the only physical region is, for me, what's above the horizon. So instead, I consider what I like to call the cosmological de Sitter group. Sometimes I see people calling it the boostless de Sitter group as well. And it looks like this. So these are the rotations. These here are the spatial translations. And this is the closest you get to a time translation in the zeta, which is actually sort of a dilation. You can actually let time runs by as long as you also consider that the universe is expanded in its hands. You have to stretch things as well. So this group here, the DMP group, is a very direct generalization of this cosmological de Sitter group. So you have rotations going to rotations, you have this factor of R going to functions, you have this factor of R going to functions. So it is more or less a natural way. But what I found interesting when I was first studying these things is that you have this thing in which BMS gets you to SO plus 3.1 times sin infinity S2, while DMP gets you to this SO3 and two products with infinity. And there is this silly question of why exactly are these groups different instead of being more similar? And in particular, I know that I can try to exploit this group here to pursue something like a conformal field theory on the boundary or something like that. But this guy is insufficient. It doesn't really give me room to look for a local group, a local algebra or something like that. So I would like to try to get a way of increasing this guy. And the way we tried to approach this question was by trying to describe both groups in a unified way. And the way we did that was by thinking about the sky as a Killing horizon. So a Killing horizon in general relativity is a new hypersurface which obeys some of the isometries of the spacetime. It is preserved by some of the isometries of the spacetime. So for instance, if I consider Minkowski I can have, for example, this surfaces here, which are x equals t and x equals minus t. The surfaces are preserved by boosts. So a boost in here would act in this way. Over here, and over here. And these specific surfaces are preserved by this structure. So they actually are sort of like symmetry invariant, and we call them a Killing horizon. This actually happens in many other spacetimes. So for instance, in the sitter, these surfaces in the middle, the cosmological horizons, are Killing horizons. In Schwarzschild spacetime, the black hole horizon is a Killing horizon, and so on. And these are very important structures when you work in quantum field theory in curved spacetime, because they are related to the Unruh effects and to formality effects in quantum field theory. So what we try to do is, well, we already know that in the sitter, in more general spacetimes considered by Dappiaggi, Moretti, and Pinamonti, this horizon is a Killing horizon. So what if we can try to think of infinity in asymptotically defined spacetimes in the same way? And what turns out is that it can actually do that, because if I start over here, what I can do here is that I have this sort of symmetries that are going to behave just like in Minkowski. Then what I can do at infinity is I can just use time translations and push the time translations to infinity and see that at infinity they become a symmetry. They are in the BMS group, and they preserve exactly this structure at infinity. So infinity is, in a sense, a limiting notion of a Killing horizon. When I take the limit in which I'm pushing this time translation vector field to infinity, it behaves exactly as a Killing horizon would. And in this sense, I can think of infinity as what I like to call an asymptotic conformal Killing horizon. Now, what these words mean is Killing horizon means this invariant and some sort of symmetry. Conformal means that I'm having to take a conformal transformation to push my vector field to infinity. And asymptotic means that this holds in a limiting sense. So it is not a genuine Killing horizon in the sense that it is not invariant and that isometry is of a neighborhood of the horizon, but rather as I approach the horizon, it becomes more and more symmetric in a limiting sense. As I take the limit, this gets more and more symmetric. Now, when I take this sorts of structures, I have a few very natural notions that I can define on them. First of all, since I have here this manifold that is some manifold inside my spacetime, I can immediately get some manifold associated with it, which I'm going to call N. So this has some manifold structure. I can also get some induced metric. I usually call it HEB. So this is just the metric that you get when you restrict attention to this surface. Maybe you need some help from a conformal transformation to get to this metric, depending on what exactly are the definitions you're using. And you get some vector field, which is the Killing vector field associated to this horizon. So it is the symmetry under which this horizon is invariant. Now, instead of working with this specific guy here, I usually prefer to rescale it. So I define some NA equals some function times XA, and I impose that NA should be geodesic. Because in this way, this N remembers what was the metric structure of the surrounding spacetime. So we get this triple here. Now, this triple forms what we call a Carolian structure, which is a sort of manifold that is not really pseudo-Riemannian, but rather it is something more different. It has this null direction. So this here is a metric. This is, for example, a three-dimensional manifold with a two-dimensional metric. And this is the remaining direction. This is the direction that is missing in this metric. So for instance, maybe my metric looks, usually at an infinity, it looks like this. I have 0 times the u squared plus the metric on the sphere. So this is a three-dimensional manifold because I have this u over here, but my metric is two-dimensional. It only has the components along the sphere. And I have this vector here, which is along the other direction. Now, this structure is defined up to some invariance, and what we find is exactly that for this sort of structures, the invariance, the ambiguity in defining the structure is going to be something along the lines of this group here. Which I usually call the CTH group. In this case, I am assuming that my horizon has the form R times a sphere, but I can make more general things. This could be traded for a more general cross-section sigma. And this here generalizes both BMS and DMP. Now, for the sitter specifically, I don't have all of this conformal freedom to get all of this group. When I'm working in the sitter, indeed, you only get something like this, or a construction doesn't really show how you could increase DMP to get a conformal group, which was one of our original goals, but it didn't really work that way. But it does show you how you can get this symmetry group at infinity. And this is particularly interesting because while most analysis that work with infrared stuff start by fixing a theorem, so for example, a theory, for example, they fix GR and then compute symmetries, etc. We didn't do that. We actually just fixed something about differential geometry. We assumed that spacetime is described by a metric or something like that. Then we compute the symmetries by using differential geometrical methods, and eventually got to this group. So this is a larger group than the BMS, but it has this advantage that I never told my math that I wanted to think about general relativity or any other theory of gravity, which means that maybe this guy here has some physical meaning that I can explore later. So I know, for example, that when I take all of this guy over here, yes, the standard BMS group, this is going to give me memory on the plus and cross polarizations on gravitational waves, which are the ones I have in general relativity. So our guess for now, which is what we're looking right now and investigating, is that since we have here this extra factor, which behaves just like dilations would, this guy here could signal that by looking at symmetries at infinity, we're getting memory at other GW polarizations. So for instance, in GR, there are no other gravitational wave polarizations, but we never told the calculations that we wanted to consider GR. We're trying to go for something more general. So in GR, we only get the plus and cross, which are oscillations that look like this. So you have plus going like this, and you have cross going like this. But it can also have, in modified theories of gravity, something that we call transverse briefing null, which is going to be some oscillation that looks like this. This, for example, is what you get with a dilaton field. Either in the simplest way is what we call Brent-Dicke gravity, which is just a modification of general relativity, which promotes the Newton constant to this new field, which we call the dilaton. And these sorts of things also appear, for instance, in string theory as one of the possible modes of oscillation of a string. Which means that when you take a look at symmetries from this more geometrical perspective, you have these advantages in which you can unify BMS and DMP in a more natural way and understand why exactly they look alike and why exactly they are different. And this is all related to whether, when you take those symmetries over here, whether your horizon is something that has isometric or conformorphic cross-section. So if I take this cross-section here and this cross-section here, are these guys isometric or merely conformal to each other? And depending on this is what we're going to give you the freedom between one or the other. we get a larger group, actually, which is this asymptotic group. And this suggests in a very natural way that we should look at dilaton memory or something that looks like it. And it also gives symmetries on a relatively arbitrary theory of gravity, in the sense that I never fixed my theory of gravity. I'm working only with geometry and letting geometry lead the way. And this works in principle in any dimension. So I don't have to fix a specific dimension to consider these things. I don't have to fix a theory of gravity. And I don't have to fix a cross-section. So for instance, the asymptotic group in a more general case, in which my horizon has the form r times sigma, is just going to be the conformal group on this cross-section sigma times functions on sigma. And this is perfectly well defined as long as you're working with asymptotic conformal horizons, regardless of what exactly is this cross-section that you have here. It could be something more general, such as maybe the plane, maybe a torus, maybe some order construction, maybe something with more dimensions. Maybe you're working instead of a two-dimensional sphere. Maybe you're working with, I don't know, a d-dimensional sphere, a d minus two-dimensional sphere, or something like that, which invites you to a very natural way of considering generalized symmetries on higher dimensions. And we're still investigating what are all the consequences of this, because, for instance, the consequences of BMS come by means of the soft theorem and of the memory effect. But at this point, it already suggests a lot that we may be able to find an interpretation for memory of a dilaton field, which is something that, as far as I know, is still very foggy in the literature. People have worked with memory of a dilaton field before, but it was never very clear how exactly you should interpret it. And this picture with what we call superdilations, which are this extra factor here, seems to give a very natural explanation, among other things, such as, for example, trying to consider bifurcate horizons and see whether this leads to more specific notions of symmetry. So, for example, if I take no infinity here, usually when you draw a Minkowski diagram, you can actually draw it hugged on a cylinder. And it's going to look something like this. So you have this cross here, in which the horizons touch, and they bifurcate. So you have, it looks just like a light cone at the origin, but this point is actually at infinity. And trying to understand this thing may give some more information about what happens at infinity. The structure based on symmetries can give a more tight constraint on how the limits and behavior should work, among other things, such as, for example, something we're curious about investigating as well, is what exactly we can do with bootstrapping ideas. So, for instance, the DMP group was originally considered so we can pick spacetimes that look like the sitter, that have this best boundary here, and use the symmetries on this boundary to fix a quantum state that obeys the symmetries when you push it from the bulk back to this boundary. And in this way, DMP managed to make this construction of interesting quantum states in quantum field theoretical spacetime, which is often a very difficult thing to do in algebraic quantum field theory and QFT spacetimes in general. So this perspective seems to be very interesting in investigating many properties of infrared physics by using this inspiration from topics that come from all around the place. So that draw a little bit of ideas from general relativity in the form of Killing horizons. They draw some ideas from algebraic quantum field theory in the form of the DMP group and this possible bootstrap approach, among other ideas. And we're excited to see where exactly it can lead us to. So I think I'll stop here, and thank you very much for your attention.
Thank you, Nick. Let me stop the